Hello, I'd like to take this opportunity to welcome you. Welcome you to today's encore presentation. As you can see, talks about automation ready, 5-axis productivity, and basically the base machine is the Makino DA300. I'd like to point out to you there on the right-hand side, there's a chat box with question and answers. As we're going through this today, if you have questions, feel free to enter those in, and hopefully we'll have time at the end here. We'll get as many of the questions as we can. I'd also like to remind you that if you signed up for this Experience Center, you should be, if you registered, you should be getting a follow-up email, and there'll be a link. So if there's folks you want to share this with, you'll have that. You can also show up then at that point in time with any other questions. We'll try to answer those. And also, this in a couple days will be posted to www.makino.com, so you'll have the opportunity to follow up there. So at this point in time, I'd like to start the presentation. Morning. I'd like to thank you for joining us this morning in the Makino Experience Center. We're going to talk about the DA300. We appreciate you joining us for about 30 minutes here. We're going to try and keep it short, sweet, and right to the point. Introductions. My name is Bill Howard. I'm the product line manager here at Makino for Vertical Machining Centers. Today we're going to talk about the DA300. We're actually going to demonstrate it live on the floor about 50 feet out here outside the EC Center. We're going to have live machine overview. We're going to talk about how we built it and why we built it that way. We're going to cut back and forth with live on machine cameras. And then we're going to reserve a little bit of time at the end for questions and answers and a wrap up. Sorry, got to re-educate my finger. There's two pictures here. The top picture is at Makino Mason. That's our corporate headquarters. That's actually where I'm at. There are two EC centers here. This is EC Experience Center number 1. There's Experience Center number 2 right down the hall. This is Auburn Hills. That's in Michigan, north of Detroit. And we actually have 2 Experience Centers there as well. So I should have mentioned earlier, I'm in the Experience Center, but I've got Ken Werbeck out on the shop floor, and he's going to be out there with the machine. So I should have mentioned Ken. Matter of fact, there's Ken now. Wave, Ken. Say hi to everybody. The right side of the screen, that's in here in the Experience Center. The left side of the screen, that's out there with Ken. And one of the things you'll notice right away is the picture I have in here is different than what Ken's showing you. That's because this is the standard standalone machine. Actually, what Ken has on the front there, we've added automation. It's an Aroa Robot Easy automation. So what I'm going to do, show you kind of the capability of the EC Center. I'm going to maximize on Ken's side of the screen. You can see in the work zone there that the machine is running. And here's the Robot Easy on the front. And I'm going to ask Ken to zoom in on some of the parts that we've got out there that you would typically see on a DA300. Okay, thanks, Ken. Up in the top right-hand corner there, that's a die-cast aluminum steering housing. And you'll notice it's got features all the way around the part on oddball angles, cross-section, intersecting holes. That's a classic part where you would set it up, work around it on 5 faces, tilt it over so you have compound angle, multiple side access, 5-face machining. A lot of hydraulic components have similar type machining. The next part down, that's also a die-cast aluminum automotive type part. That is a pump cover. And there's, again, a lot of machining around the periphery, angled holes. So that would, again, be typical where you could set up multiple parts and work your way around. The bottom right corner is a cast steel or steel part, and basically what we're looking at there, it's kind of a simulation of the machining that you might find in an engine component. So, you got holes, angled holes, compound angles cutting through there, various surfaces. Again, the objective will be to set it up, work around that part, get those angled holes down inside, all in one setup to make it as accurate as possible. In the middle, at the very top of the screen, that's actually a knee component. It is a cobalt chrome type part. And the key thing there is to look at all the contoured matching and blending surfaces. Very good surface finish, very good features. The next part down through the center, there's 3 parts in a row there: the raw material, the machine in process, and the final part. That's actually a hip or fracture management plate for your hip. And that's actually in titanium. So you can see multiple steps in that part. And the very bottom center, that's a fracture management plate. Typically that would be in like your spine or something like that. You can see here's the original setup. We take and machine the part so that we can put it into the fixture. Thanks, Ken. There's the final part. You notice it's got no features, no flat features on it anywhere. The whole part is round, compound angle holes, and we make the part on the stock, and then the bottom little piece here, that's where we separate the part from the actual material itself. And that's titanium, and again, fracture management plate. Over along the left-hand side of the screen, there's at the top 2 aluminum applications. The one at the very top is showing angled flat surfaces all the way around the diameter with angled holes. So showing the exercising of the A and C axes. In the middle, it's the kind of the same thing. We got a lot of periphery machining, so 5-face milling again, tilt it over, work it around. Plus, there you go. Plus a lot of big angled holes and intersecting holes through the bottom. So 5-face machining. And in the bottom corner, that's a block of titanium. And then below it is a bracket, an aerospace bracket that we've made. So that gives you an idea of the types of work. Thanks, Ken. So you can see that solid block right there behind the part. We whittled all of that, we cut all that out in order to make that angle bracket. Okay, Ken, I'm going to take control back in here, and we're going to talk a little bit about some of the features of the DA300 and how and why they came about. Let's talk about the structure. What we did was we took the best features of the D300 machine, the tilt rotary table, the 5-axis and SGI control, the accuracy and thermal management of the D300 series machines. And what we added to that was the productivity features of the horizontal, the A51NX, probably the most popular horizontal machining center in the market today. Things like a slanted column that allows the cutting forces to be better transferred down into the column. It lightens up the carrier for speed, act, and depth. A 60-tool tool magazine. So 60 tools on a vertical machining center, a lot of tools. The machine dynamics, the speed and accuracy of an A51. Chip management, we'll show you that in detail. And then intelligent functions like inertial active compensation for both the tilt rotary axis and the tool magazine. Basic travels, got to give you an idea, it's a little bigger than a bread box. We're looking at 450 and X 17.7, 620 and Y 25.6, D is 500, 19.68. The A axis is the tilt axis. it tilts away from the operator 30 degrees and towards the operator 120. So there's a total there of 150 degrees. And then a full 360 rotation. Well, how do we build the machine? What's the structure? Here we go. Big, heavy machine bed, 6-point leveling, that forms the foundation. The tilt trunnion table is on the y-axis. You'll see that here in a second. That gives us our A and C. We have a bridge-style column with a terraced guideways on the top. Again, that allows us to minimize the carrier, speed up that carrier, make it faster, and also you'll see accessibility into the part. There's your X and Z on the column. Now the other thing is the y-axis, and you'll see that here in a minute, the y-axis with the tilt trunnion table moves back under the column. So that shortens up all your reaches and distances. Good, stiff, rigid, very well cutting machine. There's your C-axis, 150 RPM. The A-axis is 100 RPM. And you're looking at DD motor design. So there's all of your basic travels and the configuration and layout of the machine. Talk about basic workpiece size. You're looking at about a 450 millimeter diameter. We're going to show you a pallet changing machine. So about 300 millimeters above the pallet and about 500 pounds. What we did here was we just took the basic travels and tilt rotary and laid it out on, so that you get an idea. Here's that plus 120. There's your minus 30. Total of 150 for the A. Obviously the C is on top of there. There's your X, your Y, and your Z-axis stroke laid around that maximum workpiece. Now, you have distance, you have velocity, which is the rate of change of distance, then you have acceleration, which is the rate of change of velocity, and then you have jerk, the third derivative, which is the rate of change of acceleration. Jerk is something that you want to avoid on machine tools. So what we're going to show you here is a quick video. You're going to see somebody come in and stand a coin on its edge. In the distance, you see motion. What that motion is, that's the A-axis and C-axis. You're looking at 150 RPM on the C, 100 RPM on the A with a full 500-pound pallet load. And you notice that coin never moved. So that's the control of the motion, the acceleration, velocities on the machine. Outstanding positioning accuracies, repeatabilities, the surface finishes, matches, and blends. Precision, let's talk about how the machine is built. It has scale feedback. Not only scale feedback, it's Mori scale. It's an optical, 0.05 micron optical scale. So it's non-contacting, it's non-wear. It's going to be that kind of accuracy for the life of the machine. We have linear guideways. We talked about the terrace. There's your X, your Z, and your Y. Those are roller guides. That gives us speeds up to 60 meters a minute or 2,400 inches. And we have ACK and DEC 0.8G to 1.0. The tilt and rotary are DD motors. So A-axis, tilt, DD motor, C-axis. 0.0001 degree rotary encoders, so extremely accurate and very fast to match up with the travels X, Y, and Z. Now, what I'm going to show you here is just a real quick view of the speed of the machine. There's your X, there's your Z, there's A and C and Y. Now, in a second here, we're going to look at the speed of that thing. Now we've put a camera, a GoPro on the pallet itself, the table, and we're going to spin your head around just to give you some appreciation for the speed and capability, the kinematics. All of this is driving out any non-cut time. So it reduces your cycle time, increases your profitability. Now let's talk about thermals. You might say, well, how do you control temperature on the machine? We have massive cast iron. We have a thermocouple in this cast iron, and we're constantly monitoring the temperature of the bed. We have an oilmatic unit. We use that to maintain this feed within 2 degrees of the temperature of the bed. So we have a jacket around the spindle. We have core-cooled ball screws and bearing packages. And we have a jacket around the DD motors for the tilt and the rotary. We recoup all that, take it back to the oilmatic unit. And the key thing here is we're maintaining the temperature of all these elements to within 2 degrees of the temperature of the bed. In effect, we're creating an ambient manufacturing zone of all of those components to get rid of thermal impact and thermal effects upon your part cycle. Talk about the spindle briefly. 30 horsepower, 15 continuous, 20,000 RPM. It's an HSK A63. It's an air oil lubrication with the jacket that we just talked about. You're looking at 70 millimeter, 2.76 inch diameter, inner diameter for the lower bearings. You're looking at 0 to 20,000 RPM in 1.5 seconds. Now, I'm going to show you a little video, and I apologize up front for the video. What we want to show you here is the capability of the machine to hog out, and in this particular case, it's an aluminum electrical box. Unfortunately, the minute we start hogging out, we got to turn a lot of coolant on to get the chips out. So you're not going to see much other than what it looks like when you start and what it looks like when we finish the hogging cuts. So here we go. As I said, this is an aluminum electrical box. There's what it looks like. It comes from a solid block of aluminum. And in a second here, you're going to see, take a look at what it looks like right now. Now all the coolant's going to come on, so it's really going to mess up your image and your view. But just keep your eye on it for a second. I promise we're going to turn the coolant off here and show you what we've accomplished in this little short period of time. There you go. Look at all the aluminum that's been hogged out of there. Now we've got a face mill, and you're going to see an example of 5-side machining, top and in the sides, and TCP, tool center point and control. Multiple sides. Now we're going to change tools. We're going to change to a drill. Again, we're going to do multiple sides, but you'll notice that motion. That's GI drilling. We've moved or changed the loop or the process to get out all of the non-essential, non-cut times. Now we're going to go to an end mill, and again, we're going to work on multiple sides of the part. There we go. And again, you're using TCP as well, tool center point control. So that gives you an idea of GI drilling, GI milling, and also the hogging capability of that machine. Now, what allows us to do that on that machine? Well, what you have here on the left side of the machine is the power curve. Notice the power. You've got full power, about 3,500 RPM, all the way up through about 15,000, and still very good power all the way up to 20,000 RPM. Same thing with torque. Very good torque through the mid-range, and we maintain torque all the way up to 20,000 RPM. So you have a good blend of power, torque, and high RPM for a lot of those small matches and blends or small drill type tools. Very, very productively laid out and built, executed machine. Now I'm going to talk in here for a minute about the tool changer. You're looking at a solid model. As that model rotates, look in the front. You'll see the robot shutter. That'll give you a view of it as it rotates around. I'm going to change to the other side here for a second. Here you go. There's the robot shutter. This is the 60 tool magazine, the access door for loading and unloading tools, just like an A51NX. There's your tool changer. Tool comes down, there's your double arm, takes it in, puts it into the spindle. 60 tool standard up to 254. We're going to go out to Ken here in a minute and see that. 70 tools, a 7 millimeter diameter nominal, 140 millimeter with adjacent pockets empty, 300 millimeters long, 17.6 pounds, 3.5 seconds chip to chip. This is showing actual video. There's the tool going down. You notice that flash. What that flash is a digital camera. What we're doing, and there's the tool going into the spindle, door closes, take a picture of the tool coming back as well. We're taking a digital image of the tool as it goes into the work zone and when it comes back. We're comparing that digital image to the tool length and tool diameter that's stored in the control and the H&D values. The idea here is we want to check and make sure that we're not bringing a tool out that's pulled out of the holder, pushed into the holder, broken. So we're assuring the quality of your part, but we're doing it in the tool magazine. So there's no impact upon cycle time. And again, it protects the integrity of your working of your part. Now, sorry, I should have, I need to make my screen small. And what we want to do is we want to make Ken's screen big, which means we're now out in the show. Sorry. Like I said, I got to re-educate my finger every now and then. I want to make this side over here big. What we're looking at is next to the 60 tool magazine, and you can see the 60 tool magazine there in the distance, we can add in the field a 200 tool expansion. So you can see a rack over here with tools on it. Here's the robot shutter. And there's a rack over there with tools on it. And the robot basically runs up and down between these racks and will grab tools and put them over into the 60 tool drum and feed them into the machine. There in the distance, you can see the 60 tool drum. And again, you can see some of the racks. The robot's right here. So like I said, that robot goes up and down between the racks, grabs tool, brings it over, puts it into the 60 tool magazine, and then can feed that into the machine center. Okay, Ken, thanks. We'll be back in a minute. By the way, Ken's out there cutting apart, and we've kind of ignored that. This is a camera actually on the machine, and you can see he's going down. It's a little aluminum part. It's got machining on all four faces in the top. And you'll notice there's 3 chucks on that particular pallet. That allows us to work on 3 parts simultaneously, all 4 sides and the top. That part has a dome, kind of tough to see, but on the very top of it, there's a dome on that part. So that is a full 5-axis machining, matching and blending. There's also 2 cylinders sticking up. You can see them there. And on the top of those cylinders, there's a cone. That's simulating an NAS 979 test for 5-axis machining of tapered surface. So Ken's out there running this while we're in here talking. I'm going to maximize in here for a second. And we're going to talk about, obviously the machine can make a lot of chips. You saw that when we ran that electrical box demo. That means we need a lot of coolant. We have base coolant. We have through spindle coolant. There are 4 nozzles around the spindle. There's 11 nozzles shower overhead. So the objective is to get all the chips washed down into the center trough and out of the machine as quickly and effectively as possible. Now, we've purposely allowed all the chips to build up here. Not very good housekeeping, but in a minute, you'll see the coolant come on, there you go, in the throat of the machine. And notice it just whisks all those chips away. Not a problem. Then you're going to see 4 nozzle flood and the 11 overhead coming on. So there you go. Now, if we move the y-axis and tilt the A, you'll see that very quickly, even though we had a very kind of bad housekeeping situation, we'll be able to clean all of those chips out of the work zone very efficiently, very effectively, very fast. Keep the machine running. That's what you want to do. Okay, so that's what we're looking at as we move the Y. You'll also notice the terrace cooling coming down the side and over here down the side. We're washing all the coolant, all the chips down into that center trough and out the back of the machine. Now, before we talk about that, I'm going to maximize Ken's side. And what he's done, he's went back. We got all those chips and coolant, and we washed them down into the central trough. The last thing we want to do is clog that up with, scrapers or whatever. So we've gone to a Henning CDF, chip disc filtration lift-up chip conveyor. Well, it's got discs along the side, so the center's open, get all that chips and coolant out of there. We pull the coolant through those discs, and we get about a 30 micron coolant purity. Then what we do, Ken's trying to move, there we go. That little silver thing there, that is a cyclonic filtration. So we take the coolant that comes through the discs on the lift-up chip conveyor, we go over and put it through that cyclonic, we end up with about a 20 micron coolant purity. Okay, Ken, I'm going to make your side small and maximize mine here for a minute. He's going to be setting up on the pallet handling system. Talk about the machine here. Basic, it's got a 300 by 340 table. And that table has 5 integral ports. One of them is an exhaust. The other 4 could be pneumatic, or you could have 2 pneumatic, 2 hydraulic. We'll show you how we use those. What we've done to the 340 by 300 table, we've put an Aroa UPCP chuck on the top of that. That's this thing right here. So now with that mounted there and plumbed up, we can change Aroa pallets and workpieces to and from the machine. That's what it looks like in here, but we're going to go out to Ken and we're going to look at it out there on the floor. This is an Aroa Robot Easy. There's actually 10 pallets on that machine, and you're looking in through the front. Here's that electrical aluminum hog out. Over there is that die-cast aluminum steering knuckle or steering block. There's 10 pallets there. Now, I'm going to ask Ken, well, you can see in the middle the robot shutter. That robot shutter comes into the machine, or robot arm, comes into the machine, picks up the workpiece, takes this out, puts it on the table. The table rotates, it picks up the next workpiece, and puts it in. So obviously this allows you to automate flow of work to and from the machine. You can have a variety of workpieces. You can run into the evening, you can run overnights and weekends. Now Ken's around to the other side. There's a door on the operator side. You can see the handle there, it opens up. That allows you accessibility to either go in and load and unload workpieces to the fixture in the automation, or literally pick the pallet up, bring it out, take the fixture off, put a new fixture on, and bring it back in. So very flexible, very capable. Okay, Ken, we're going to go away here for a minute. So that's the Robot Easy. We've also offered another type of automation. It is called the ERE80. Depending on chuck and pallet size, you could have up to 80 workpieces. It's high stack. There's a little drawer here you can see that opens and pulls out. That's where you load and unload workpieces. We've actually supplied this in a number of customers where we're sharing the ERE80 between 2 DA300s. So now you've got a small cell. You load and unload the workpieces here, and it can go to either machine. So that's the capability there. I'm going to show you, there's the robot shutter opening. Here comes the robot arm in. That's the Aroa pallet receiver plumbed into the machine. There we're coming in with a pallet and a workpiece fixture. I'm going to set it down. We're going to clamp it, actuate it. Then you're going to see the robot retreat and the shutter door close. So you can see a very quick, efficient, fast means of automating the flow of work to the machine. Let's talk about the control. It has the Pro 6 control. Pro 6 is the Makino proprietary GUI user interface. And basically, talk about it for a second. Oh, it has Collision safeguard as well, and we'll show you what that means. The design of this is very intuitive, simple. You'll notice the buttons over there. The idea is to prompt you through setting up the workpiece, entering the data, and going right into running work. Traditionally, you had point-to-point, large distances, stopping and going, acking and decking, long cut times, poor surface finish, very poor tool life. But with SGI 0.5, you'll notice we've defined a user of tolerance. We've run very quick, very efficiently. We reduce cutting time, better surface matches and blending. So let's compare the two, conventional, new. Keep an eye on the speedometer, particularly on the conventional side. See, ack and deck and up and down. We're done. Run a constant speed, obviously quicker, faster, smoother, better surface finish, much better part in less time. Now, collision safeguard. When you start building 5-axis machines, you have to recognize there's the potential of the machine actually impacting itself. Look at the red tool. Keep your eyes on that red tool. We're cutting around. Now we're going to index the tilting axis, and the red tool just disappeared from the image. Now we're going to do the same thing with collision safeguard working. Same cutting and see, indexing the part around. Now we're going to try and do that A-axis position. It stopped. Oh, it's generated an alarm. Well, if we hit the button, the alarm will open up. And it'll tell us, basically, as you were working around that part, you didn't pull Z up enough to index A, and you ran the part into the tool. Well, like I said, we originally come up with this concept when we started building 5-axis machines. We recognized that the table and the spindle, you have to protect the machine from hurting itself. So what's going on is back behind there, there's a solid model that's got the machine work zone, and it's making sure that the machine doesn't try to run the spindle into the table or the table into the spindle. Thinking about that, we recognize that if the customer's willing to put a solid model in there of the part, a solid model of the fixture, we know where it's at, G54, 55, 50, wherever you put it on the machine. And a solid model for each tool. We know the tool length, the tool diameter. So now we can run all of that live in the background and provide collision avoidance. So we're protecting not only the investment in the machine tool, the investment in the workpiece, the fixtures, the injured tool. That ends the formal presentation. I'm open for questions, and we're going to bring Ken back.
Yeah, I've got a couple questions. One that came in here just a minute ago. I'll just read the question. It says, does the technology exist so an HD image and or laser could determine tool life? Well, there's a couple things mixed together there. Does technology exist? Yes, and it exists for both an HD image, so you have a high definition camera, or a laser. Unfortunately, both of those, what they're looking for is they're looking for broken tool, not necessarily tool life. So yes, you can have a high definition camera. The tool has to be in the spindle because you want to be rotating the tool around and taking high definition images. And then it can basically determine if the tool is broken, or if it's sucked back up in the holder, or if it's come out of the holder, or if it's chipped. So therefore, that technology exists, and we can do that on some of our die mold machines. By the same token, with today's ATL, automatic tool length measurement laser, we've also gotten to the technology where, again, the tools in the spindle, you can rotate the tool and basically determine cracked or chipped or broken tools. So the difference there in the terminology is, yes, the technology exists for high definition images and also for laser, but it's not looking for tool life. It's looking for broken, cracked, chipped tools. Couple downsides of that is, obviously, it has to be in the spindle, so you're taking production time in order to do that. Now, again, in a die mold world, when that tool's in there for hours and hours and hours, that's maybe not as expensive to you part cycle time wise as it would be on a high production. As far as tool life, each tool, you can set up a basically a cutting level that tool, the amperage the spindle should draw when that tool is cutting normally. We can monitor that, and then based upon when it gets to a certain level, we can declare that tool's life has been used. We can set minutes. And again, you can go in and say, okay, this tool's worked 200 minutes. And as you get to 200 minutes, if you're cutting with it, it'll allow you to finish the cut, but then it'll immediately alarm that tool as a tool life alarm, and then you can have backups or redundancy set up so it allows you to pull a secondary or backup tool. So there's a little difference there between whether we're looking for cracked, broken, chip tools versus tool life. So I just wanted to explain that. Also, some questions that had come in about the tool magazine expandability. The ATC 60 is the standard. We can add another ATC 60 to get you to 118, or the one that Ken showed you out here in the showroom, add to the ATC 60 standard, ATC 200 expansion would get you to 254. So we can go from 60 to 118 to 240, and those are field expandable. So you could start out with the 60 tool machine and then in the field expand the tool capability. Same thing with the automation. The automation that we showed you out here, the Robot Easy or the ERC 80, that you can start with a standalone machine, single pallet, and then as you expand your work, you can go out and add in the field either one of those Aroa units. The Aroa ERC 80 is actually shared between two machines. So you have the ability to start, I don't want to say small, but start with a standalone machine, but then add tooling and add work pieces as your shop volume and differential number of parts increases. I don't see any other questions right now, so I'd like to thank you for joining us today for this encore presentation of the DA300 Automation Ready 5-Axis Productivity DA300. And again, I'd like to remind you, if you registered for this Experience Center, you should be receiving in the next couple of days an email with have a link. So if you have other folks that you want to see this or share it around, you'll be able to do that. And in a couple days, this will be posted to the archive at www.makino.com. Once again, thank you very much for joining us today at this Makino Experience Center.